Hi everyone, this is our project. We're doing an analysis on the Falkirk Wheel. Next slide, please. This is the simulation breakdown that we chose to do. Next slide, please. The first analysis was a modal analysis on the arms of the wheel, and the purpose of this was to minimize the vibration of the arms during operation. These are the parameters that I had, and the design iteration that I chose to do was to change the arm thickness from 6 meters to 10 meters in increments of 2 meters, and to change the radius at the end of the arms from 26 meters to 30 meters in increments of 2 meters. Some examples of this are shown on the right. The photo on the left is 6 meters. The photo on the right is 10 meters. Next slide, please. Here are the results that I acquired. From this, we can conclude that an arm thickness of 6 meters would yield the lowest vibration, and the radius at the end of the arms of 30 meters would yield the lowest vibration as well. Next slide, please.
So static and displacement analysis was done to minimize the stress and deflection of the individual gondolas. Its material was set to be plain carbon steel, and it's fixed near the edge faces on the outer side of the gondola where it makes contact with the arms. There was a 250-ton distributed load applied to the top of the gondola, which simulates the combined weight of the water and the boat at any given time. The design iteration included varying the thickness of the barriers and the length of the gondola longwise. Its original barrier thickness was 1.127 meters, and its original length was 33.842 meters, which represents the actual size of the gondola. As depicted from the analysis, it was determined that increasing the barrier thickness and decreasing the length would result in lower maximum stress and displacement values, as depicted in the next slide. So the optimal dimensions of the barrier thickness and length would be 1.5 meters and 30 meters respectively. Next slide, please.
So we did buckling analysis on the upper supports to show the force that is coming from the aqueducts. The material chosen was a plain carbon steel to simulate rebarb that is part of the construction with the concrete. And the loads and boundary conditions used is 2,451 Newton on the contacts for the aqueducts and fixed on the bottom face. And this simulates the 250 tons that is from the aqueducts, and it's scaled down to 1,000th for our model purposes. And for my design iterations, it shows 5 millimeter for thickness and 17 millimeters for inner radius as the base values. I found that the buckling factor of safety increases as the thickness goes up, and it lowers when the radius goes up.
So the fatigue analysis for the lower support is to observe the damage to the support over time, also compare the maximum life cycle between each iteration. The material is ballistic steel. The design iteration is the leg size and thickness, and the boundary condition on the bottom plate, also the bottom face of the legs. The load is applied on the shoulder to simulate the weight from the wing and arm, and also the centrifugal force is simulate when the wing is rotating. Next slide, please. So the table, you can see the iteration when the leg size is increased, the maximum damage done over time is decreased, and also when as thickness goes up, the maximum life cycles will increase, and so also the damage over time decrease. And if you go to next slide, please. So as you can see, for the two different iteration, the even though there's most the area is with really low damage over time, except the part that it's sharp edge that could be caused by singularity, and that it could be fixed by just making the sharp edge round. The next slide, please.
For the thermal analysis, the purpose is to observe the heat relation between the bearings and the main rod of the wheel. The material I used was stainless steel. For this, I used a thermal analysis to get the heat flux of the wheel. My loads were a convection going to the rod with a convection coefficient of 2.5 to imitate the relation between the exposed wheel and air. I put a temperature load of 80 degrees Celsius to imitate the friction between the rod and bearings. My design iteration here was changing the diameter and the length of the rod. This iteration is scaled down from the actual wheel. Next slide, please. On the top left is the heat flux plot and below is the temperature plot. One takeaway that I noticed is that increasing the diameter and length increased the overall heat flux of the design, while there were not much differences between the max temperature of the system, as they all stayed around the 350 Kelvin range. And with that, thank you.
Thank you.
Thanks.